Hello, let's do this problem from section 5.4 in your Math 253 class. Here we have a triple integral over a solid E of y dv, where the solid E is bounded by the parabolic cylinder z is equal to x squared, and the planes y is equal to 0 and z is equal to 11 minus 4y. All right, first thing we want to try to do is visualize this. I know it's kind of difficult to visualize things in 3 dimensions, but we have to get a handle of all those different types of surfaces that we've already studied. And this would be one of the reasons why we're going to be able to do that. First of all, the parabolic cylinder is on the xz plane. So on the xz plane, we would draw a parabola, and there's no y variable in it. So this is going to get swept along the y-axis. And we can imagine the parabola looking something like this. It's being cut off by the plane y is equal to 0. So the plane y is equal to 0 is all the way here at the end. Well, at the end of where the xz plane happens. So already we can have this as one of the boundaries. So we know that we're not going to get any more negative in the y direction. Now the other plane is a little tricky, but it is still a cylinder in terms of the variables. There's a y and a z in there, and there are no x's. So that means on the yz plane, we can draw this line. This is just a line, 11 minus 4x. So it has a y or a z intercept of 11. And it has a slope of -4. So we can imagine on the plane, it'll be going down, down this way. And as it goes down that way, it gets swept along the y-axis. So we can imagine a tilted plane happening here. It looks quite confusing for sure, but it looks like it'll intersect here, up here somewhere, and we have the y is equal to 0 plane covering it. And then this plane looks like it'll slice through at an angle. So it looks like we're going to get a little bit of an angle that goes down like this. So I don't know if we could see that. Let me see if I could try to redraw it here. Let's try to redraw that one again. So this is the y is equal to 0 plane, and it runs along here on the y-axis, and then it gets cut by another plane that goes like this. If you can't see that very well, we will actually graph this to take a look at how the graph of this thing looks like. I guess we can do that now. We can take out our calcplot 3D and plot those points. We got z is equal to x squared, which is our parabolic cylinder that we were talking about. We have y is equal to 0. I'll do that as an implicit surface. And we have another z function. We could do an implicit surface, but since z is already solved for by itself, we'll just put in z is equal to f of xy function. Now, I'm not seeing that here, so I think if we zoom out, we'll see it a little bit better. And here it goes. There's that little wedge thing that we were just talking about, and the slice of that function going up. And one more way to visualize this is to actually draw what's called a region. And for us to do this, we need to know essentially the limits of integration for this. So before we draw this region, let's see if we can figure out how we're going to integrate this. All right, so we will probably look at this with a z first. And let's set up our integral where it's the z that's coming first, and then we'll figure out whether it's the x or the y later. I'm looking at the z because a couple of surfaces that came up here has z's equal to associated with it. So if I draw a line parallel to the z-axis going through the region, it looks like I would hit the region here at the bottom at x squared, and then I would get out of the region on this plane 11 minus 4y. So those look like they would be good limits for your z-axis. Now, once we have that, the other important thing that we're going to need would be the shadow that this is going to make on the xy plane. So what we need to do is look at what the shadow is here on the xy plane. And it looks like it'll be some sort of a parabola shape. But how can we find that? I think what we're going to be interested in doing is we're going to let some of these things equal each other to see what we can get. Well, the z's already here look like they intersect at this parabola, or both of these things intersect at this parabolic shape over here. So we have z is equal to x squared, and we have z is equal to 11 minus 4y. So why don't we set them equal to each other and see what we get? We're going to get x squared is equal to 11 minus 4y. It looks like y would be a good thing to solve for. So this would be y equals, that would be a negative 1/4. And then x squared minus 11. So bring the 11 over, divide by negative 4, and then you get y by itself. So this looks like it's on the xy plane. It would be there's a negative in front of the x squared, so it'll be an upside down parabola that probably will be hitting the y-axis at positive 11 over 4. And then it would be downward parabola. You can kind of see that parabola here. You can also see it here as a shadow. That's a little tougher to see because it's already a big mess there. But looking at this in 2 dimensions with just x and y to help us figure out our x and y components, this looks like it's of a type 1 region. I drew a line. Maybe I'll draw it in a different color, but drawing a line parallel to the y-axis would give me my region, I think. So we'll do y first and then x last. So if we draw that line parallel to the y-axis, we would enter through this region at y is equal to 0, and then we would exit through that region at this parabola, negative 1/4, comma, or times x squared minus 11. And then now the last bit that we need are the limits for x, which should be constants. And we essentially want to find out where this thing hits the y-axis or the x-axis by setting y equal to 0. So when y is equal to 0, we're going to have this could cancel. Well, let's write it out. 0 is equal to negative 1/4, x squared minus 11. So this will cancel. You get negative 11 on the other side, positive 11 on the other side. So x is equal to plus and minus square root of 11. So negative square root of 11, positive square root of 11 would be your limits. All right. So now that we have that, let's see if we can use this information to create our region. And this is another good way to double check that what you're doing is actually correct. So I'm gonna unclick all this and it's gonna take a look at our region. And our region starts off on the XY plane with the limits for y. So I think we had a negative 1/4, and I'll put the 1/4 in parentheses, x squared minus 11 inside. And the bottom was going to be 0. So these are our y limits, if you remember. The x limits were negative square root of 11. And we're going to positive square root of 11. And then here they give us the top and the bottom. Z is equal to functions. So if you remember, the top was 11 minus 4x, or 4y, that was the plane. And then the bottom was the x squared parabolic cylinder. Okay, let's graph it. And here we go. Look at that. It is a nice looking region, pretty much like that wedge that we were talking about. And by knowing your limits for X, Y, and Z, you're kind of setting this up to be able to recreate the region in this drawing form. So this is a good picture to put in our notes just to compare with what we have. So here's that picture. And if we kind of compare it to the picture that we had earlier, we're fairly close. And it kind of looks pretty much like that. Now the shadow that's happening on the XY plane, actually, you can actually see it here. This is the shadow that we're looking at on the XY plane. And that's the picture in green that we had. This picture right here. So it kind of all matches, so it all looks good. All right, let's actually set up the integral now. And this integral is looking pretty messy. The inner integral, well, the integrand is y. The inner integral is going to be with respect to z, and z is going to go from x squared to 11 minus 4x. And then we're going to go with respect to y, and that's going to go from 0 to negative 1/4 x squared minus 11. And then finally, x is going to go from negative square root of 11 to positive square root of 11. Now, the first integrand probably isn't too bad. The second integrand might not be so bad either, but then you have to put in this negative 1/4 x squared minus 11 in for the y values, the y variable. So, and then finally, you're going to put in this negative plus and minus square root of 11 for x's after you integrate that. So that could get a little messy. Why don't we go ahead and use our graphing calculator, or our integral calculator for this. Integral. We're going to do 3 integrals. And the integrand itself is quite simple. It's just y. And then now this is where it gets a little bit complicated. Our z values are going to go from x squared to, and then I'll put this in parentheses, although I don't think you need to, just to be safe, the function 11 minus 4y. This should be 11 minus 4y. Let's make that into a y. And then we're going to go ahead and that's going to be the inner integral. The next is going to be with respect to y. And y is going to be evaluated from 0 to, this is where that big mess comes in, negative 1/4 times x squared minus 11. And so let's keep track of the parentheses, and that closes my second iterated integral. And then finally, my last integral is going to be with respect to x. And this is going to go from minus square root of 11. This is a minus square root of 11 to positive square root of 11, and we'll close that. So hopefully all that's figured out or taken care of. And if we run it, we should, I don't know if we'll get an exact value. We should be able to get an exact value, but it looks like they got us a decimal approximation, which is probably good enough. All right, so let's take that and throw it in our notes. Okay, so the main point here is not really to compute this integral. The main point is to be able to set it up using pictures and drawings and maybe computer programs to be able to visualize the region, the solid, and then come up with the limits of integration. Okay, so there you have it. Good luck.